Hi everyone, welcome back to our channel, Becoming a ROS Developer here at The Construct. My name is Rodrigo, and today we have a student, Chengjing, who's going to be showing us what he did for his project of ROS Basics in 5 days. This is a course we offer at The Construct, which is sort of the first big stepping stone we provide in order for you to get started with learning ROS. And it has a project. And in this project, you have to make a robot both in a simulation and in the real world. You have to write a program for it. So it detects a wall and it goes to follow it. It goes right next to it, and then it starts following a wall around one of our real robot labs that we have here at the Construct. And then this is done with the usage of topic publishing and subscribing, service servers and clients, and action servers and clients. And these are the main building blocks of ROS. And we ask for students to present this project in order for us to see what they've done, because it's really interesting what students can do, different ways to solve the same problem. So yeah, without further ado, hi Chengjing, how you doing?
Hi, I'm pretty good. How are you?
I'm good. So very excited to see your project. So whenever you're ready, you can start sharing your screen, and we can
Okay.
get started with the project.
Can you see the screen?
Yes, I can see it.
Okay.
Wall follow.
Yep. I'm just gonna do a slideshow, and I'll switch to the construct platform as well. So
Okay,
hi,
cool.
I'm changing. Yep. This is my real world project at the construct, the Wolffollow robot. So I'm gonna break it down to several files, and the first is the Wolffollow mechanism. The first we have a callback function to get the front and the right distance from the laser scan, because that is what we concern the most, to let the robot to follow the wall and also like detecting the wall in front of it to make it turn. So on the right side, we can see that we're trying to get the front index and the right index and the angle from them. And after that, I set a adaptive speed control for different operation, as the robot is gonna doing adjustment if it's leaving the wall. So it should be staying in the range at between 0.2 and 0.3. And if there's a if it left its track, we're gonna like adjust the speed at different level. So
Nice.
there's a normal speed that is like between 0.2 and 0.3. That's gonna maintain a higher speed. And when we're turning, we're gonna make the turn as a priority and slow down a little bit. And for adjusting the robot into the right track, it's also going on to lower speed, but not the lowest.
Okay.
And after that, we're it's basically when the distance at the front, as you can see that here, we're like we're entering a conditional loop. So the priority is turning. We don't want the front of the robot hit the wall. So if the front distance is smaller than 0.5, we're gonna apply an angular speed on the robot, and also set the robot into turn speed so it can turn. And also when the distance, or the right distance, which is marrying the distance from the robot to the wall, if it's between 0.2 and 0.3, we don't apply any angular speed and just let it speed out at normal speed. And then if it's like not in the track, then we're gonna adjust it with just speed and with different angular speed if it's leading towards the wall or going off the track. Yeah.
Okay.
After that is the find wall. Here the one of the challenges to distinguish the wall from the signs that is placed in with the robot, because they have the similar height. And so what I basically did here is a very brute force way. So basically I'm gonna walk you through the code. Sorry. Yeah. So first we're just there's the scanning. We're reading the scan from the robot, and actually getting the distance, the front and right distance. as the callback, because we're gonna read the later scan because the robot's moving and we need a callback to actually get the data. And so here, the first, we're gonna get the scan and I convert it to a array. So the idea here is that if the robot is in a well-rounded, because the robot, the Turtlebot right now has a 360 degree of scan.
I'm sorry to interrupt, Chengjing. Could you show us the environment? Because you're talking about obstacles and the robot, and since we can't see it, just to, there you go. That's
So I'm gonna move the robot a little bit.
So you're connected to the robot right now in real time.
We're connected to the robot right now.
Okay.
Yeah. I'm gonna move a little bit towards closer to the so actually the signs here is gonna be one of the factors that's gonna it's gonna block the robots from identifying if it's either a wall or a sign. And so my solution here,
I see you're placing it close to the obstacle, so that's
we're
very brave of you.
Rather than further. So there's actually a distance. So the code implementation has some fail right now. It doesn't work perfectly, but in most of cases it works. Even it's closer to the object. So I'm gonna explain the idea here. So if the robot is staying environment that is well-rounded, because we have a 360 scanning beam, the beams between each of them. So I believe we have so for every degree we have 2 beams that is shooting out the robot, if I remember that correctly.
I think
it's 1.
Yeah, you're right. Every 2 readings is 1 degree, because I think it's 720.
So every 2 reading is 1 degree. So between those 2 beams, there shouldn't be a lot of changes, right? If they're walls and things. So I'm breaking it down here, converting to an NP array for better. It's easier to processing the data.
Absolutely.
If it's 2 beams are have a distance that is greater than 0.03, which is 3 centimeters, we're gonna break it down, maybe make it a segment. So basically, if there's a small because the signs here, if you're not too close to it, the reading, the angles between the is gonna not going to be that great in the later scan. So the segment is gonna be short. So here we set a threshold to 70, which is 35 degrees in practice, and we're gonna filter out the scans that is smaller than that distance.
And that should catch the obstacles.
Yeah, that should catch these obstacles in most of the cases. Yeah, because if it's too close, maybe it's too close, 2 or 3 centimeters or 5 centimeters away, still the angles won't be too great on the scan. So that's gonna not distinguish.
Or if there's a lot of obstacles clumped together,
Yeah. So it's not gonna work in that case, and we're just gonna filter it and get the minimum distance. And here we're actually we're actually actively updating the mean distance, because it seems like when the robot starts, the distance is going to fluctuate a little bit before it actually settle down.
Okay.
Yeah.
Could I interrupt you again, Chengjing? And we've seen the fine wall sort of logic and the wall follower program. Could we see it, and then you can explain the last part? Can you launch this in the so we can see it do its thing? And while it's doing its thing, you can.
Yeah. Sorry, 1 second. So I'm gonna move it a little bit, because there's a bug. Actually, a very weird thing, because currently the minimum distance, if there's the wall that is blocking it, then it's gonna if there's a wall and the object that they're the same distance, I cannot.
It gets confused. Yes.
Yeah, it's gonna get confused.
Okay. Yeah.
Sorry, I'm just gonna move it closer to the object. Sorry. Yeah.
Don't worry.
Yep, around there, that should work. Yep. I'm just gonna launch the whole thing. We can say that the distance, the minimum distance as reporting is 0.93.
Oh yeah.
0.55, and it's actually developing, so it's gonna fluctuate a little bit. So we're like updating it and set it down after a period of time.
So what's
So
happening
yeah,
right now? This is what
the
part of?
robot is turning and it's aligning the front of the robot to the wall, and we can see that
Now
the
it's
front is
approaching
aligned
it.
with the wall, and it's moving closer to a range. So actually, there's a threshold applied to it because there's an inertia of the robot. It's not gonna stop immediately after the thing. So there's a like a threshold I set
You
to
also made
stop
it
the
slow,
inertia
which
before.
is a good idea.
Yeah, yeah. This actually takes a long time. Sorry. Yeah,
No, I mean, this is interesting. So we can talk about it without
yeah.
without
And then
having
it's
to
gonna
run.
align the right. So the minimum distance is gonna be reset here because where we change the robot position.
Yeah.
So the initial value is gonna be initialized to infinity, and right now our robot is starting to follow the wall.
And
We can
now
see
it
that
does the, wow, that's a nice controlling. That's nice.
so it's adjusting at different speeds. So there's like a priority of turning or
Yeah,
going
yeah, I can
forward.
see that. I
Yeah.
like that. I like that priority of speeds you had. And why did you do this? I mean, it looks like it's doing a really good job, but is there a particular reason why you did different speeds?
It's just I think that there's a priority for the robot to move, right? If
Right.
like too close to the wall, I want it to turn first,
Yes, instead of
rather than
moving
moving
forward.
forward.
Yeah.
Yeah. So another thing is the odometry.
Mm-hmm.
There's gonna be a so it's not gonna like moving perfect in the outer line. I can like maybe like because the wall were like between 0.2 and 0.3. If we limit that threshold, it might move better. And right now, like the lab is finished, and it's gonna shut off.
Nice.
Yeah.
Well, that's the project right there, and it was it worked perfectly.
Mm-hmm.
So you were talking about the odometry. I'm
Yeah.
assuming that's
Odometry.
related to the action server.
Yeah. Yeah.
Okay.
So I'm gonna show you here.
Yeah, perfect. Now you can
Yeah.
continue with this.
Yeah. So this is the part two, which is
Uh-huh.
basically just the step we just did. We're trying to, so there's a while loop. So if there's no scans like being posted or published, we're just gonna let it
Sleep. Okay.
run. So the time that sleep just avoid the busy waiting, trying to
Mm-hmm.
get other things working, and then we're just trying to align the front. So we can see there's a threshold applied that I can actually like make the while loop looks better because the aura kind of weird. I'm sorry for that. Yeah,
Don't
there's a
worry.
lot of optimization could be done on the code, and it just log in the minimum distance and the front distance, and we're gonna let the robot turn
Okay. Okay.
at a fixed speed. So let's 10 degree per second. Yeah, and publish the action to make it turn. And after that, so if the threshold, the distance is met, then the message is going to print the front is aligned with wall. And then, so there's a stop here, just to make the robot stop, publish 4 times to,
Mm-hmm.
because sometimes it's just,
You know,
you
that's
need
funny
to,
that you did that to publish 4 times because
uh,
just now earlier today we had a presentation and we had an issue where it seemed like it wasn't stopping. It's like and I told him just do a loop and tell it to stop 4 times or
oh
5.
yeah,
Yeah,
yeah.
it's a
So
good
yeah,
idea.
that's something I discovered when in testing. So I just decided to publish 4 times
And of
to
course,
make it.
this improves as the robots get more industrial and better. But since
Mhm.
we got what we got, this is a good idea. Yeah, good. Continue.
Yeah.
Sorry.
Yeah. So after that, we're just from distance, which was supposed to move to 0.3. So this is just to counter the inertia. I can make it smaller, so it's actually getting to the range,
Mm-hmm.
and then it's just moving forward at a slow speed. I don't want it to move too fast because inertia thing, it's gonna like push the robot too further. And after that, or stop that robot and try to align the right side. You can see that I reset the distance, the minimum distance to infinity,
Mm-hmm.
just to try to get the minimum distance again. And then it's the same thing as turning the front to align the right. Yeah.
Nice.
And this is just I'm not just gonna play this because I already demonstrated it. It's just like this the robot is closer to the object rather than the wall,
Oh,
and
okay.
it
Okay.
could work. Yeah. Yeah. Sorry, I'm just gonna go to the odometry. So the odometry consists of idea of this. So the first is um, a callback because we're reading from the odometry. It's a similar structure than with the previous code I write. We're gonna
Uh-huh.
have the XY theta initial to 0, And in the odometry callback, we're reading from the odometry. We have a subscriber that's actually subscribed to it, and setting the XY position. And for the theta, I use the SciPy to transform the quaternion to
I
your
see. Yeah, yeah. Earlier from
to the
quaternion, yeah.
XYZ. Yeah, to get the Z angle, because and it's just then it's a subscriber to call the callback. Yeah. And after that, we're gonna check the I think the most important thing is here, the to check the lap is finished. So I'm gonna show that thing a little bit. So
Yeah, because I saw that it stopped right at where it started. So
yeah,
I was wondering how you did that.
it's not, and so that was a coincidence actually. So
Oh,
in the lap down, I'm gonna go back to the previous slides later. So actually, in the lap down here in the callback, so I said, because we're like reading the odometry every 1 second here,
uh-huh.
we set the time to 8 because I don't want the lab to be finished as soon as we start. So because we're checking if like
I see.
the position of the current position is actually the starting position. So we
Right.
just
So if you set
return for
one or
always return.
something, then it
Yeah,
would be like, oh, I'm done, and it would stop.
yeah, because the robot is now like moving in perfect, like following the outer track.
Mm-hmm.
So there's gonna be a like definitely some offset. So there's gonna be a threshold applied to see check. So if it's like wasting 1, 2, 3 seconds, it's not gonna work. So we set the time to 8, but the odometry is still recorded. That doesn't matter because we're always returning to false just to tell the odometry not to finish as soon as we start. And we're gonna get so after the 8 seconds, we're gonna actually like to try to get to see the robots actually finished. We're gonna get the start X and start Y, which this is kind of redundancy. We could do an optimization because it's not gonna change. We don't need to like to initialize every callback.
Oh, but I like
And
that.
yeah, so and there's just another range that if it's within 10 centimeters of the starting, then we're gonna return true and the robot's gonna stop. Yeah.
All right.
Yeah, I'm going back to previous slides. And so basically here, so what the problem I found is still the same thing, like because the XY is not like here is like initialized to 0.
Yeah.
But I should say like I could set it to none to avoid this, but this is just to check if these 3 are the same, then like there's not the data is not published yet.
Mm-hmm.
So as soon as they start change, we're gonna start recording
Right.
the data. Yeah.
And then what did you do? I didn't see with the result of this odometry at the end.
Oh yeah, I didn't print it,
You
but
didn't get.
yeah, I suppose it's gonna so I'm gonna actually go to the code here. I didn't print it. Sorry, yeah. So the result here, we can print it. But yeah, I didn't do
So
it. Sorry.
it's stored in that result. No.
Yeah, it's it's storing here.
Okay. So
Yeah.
if we were to print that result, we would get what would we get?
Points. Yeah.
The list of the points that the robot went
traveled.
Through. Okay. Yeah. Okay. Nice. Yeah, because we saw it stop. Then I saw that message lab finished shutting off. Okay, and then you did the signal shutdown to stop everything.
Mm-hmm, yeah.
All right. Nice. Is there anything else you want to tell us?
That's pretty much it. If you have any questions.
Yes. Do you mind stopping your screen so we can see each other?
Yep.
All right. So good. So congratulations, Chengjing. Very, very nice, very clear and simple. You presented it in such a way that it was really simple, and congratulations on your program working on the real robot at the first time. That's nice. That's always nice to see. You said that it was coincidence that it stopped right in the starting position. Now I see why, because you showed us how your action server worked. Let me tell you some things that I really liked is that first that variable speed, for example, the turn, that you don't set a specific speed. I like that. That means you really thought about the problem and it's a step beyond what was asked for. So I really like that. And I also liked I call them sort of sanity checkpoints that like what you told me that you didn't have to set the X, Y, and theta to 0 every time. But I like that. And also you, for example, setting the minimum distance to infinite once you get aligned with the wall, that those things really help you, kind of establish like checkpoints in your program. And I think that's really useful. And then one thing I wanted to ask you is, so you said that it doesn't sometimes it doesn't recognize the obstacles from the walls. Could you remind me one more time how you're doing that? You're dividing it in chunks because I'm just trying to understand it. You're dividing it in chunks of 3 centimeters, and that's the circumference that you're talking about, or what is that?
So basically, like, every beam is gonna give me a distance, right? So if the two consecutive beam that is have a distance that is
Similar.
larger than 3 centimeters,
Oh,
I'm
okay.
gonna break it down to sections. So basically, there's gonna be small segments of later readings. That one block is considered.
Okay, but I still don't understand how that relates to it being either an obstacle or a wall.
Because the obstacles, considering walls and obstacles, walls are much larger than obstacles, so the reading is gonna be longer, right? So the segments if we're getting the reading, so in a ideal environment that the robot is not surrounded by those obstacles,
Right.
the walls is gonna always have longer readings than the obstacles because the obstacles are small, so
Yeah.
the angles between the beams are gonna be smaller. So I just put them into smaller segmentations and then just
Checking that 3 centimeter.
yeah,
Okay, I see what
yeah,
I see what you did there. Okay. Nice.
yeah. So yeah, one thing I didn't do is because the distance with the minimum reading could be coincidence with uh because like if the walls had the same distance as the obstacle, the robot might be confused
Right, and
later.
they'll go towards
Yeah.
the obstacles, and then we don't know what will happen.
Yeah, so
Mayhem.
for that I can actually like record the index where the walls at. So then when later checking on, so I could like
Okay,
distinguish
yeah.
the value. Yeah, I
Great. No,
think
I
that's
mean,
something I could improve on. Yeah.
yeah, so that's what I was gonna go towards. I mean, it's a really good job. You do what we asked for, but just moving forward, so you can get more familiar with things. Is you could, for example, develop a filter. So it doesn't matter where you start your robot. It'll always detect between the wall and the obstacle. And there's a bunch of filters online that you can look into it that you can apply in Python, and they work pretty well. So that's one thing. Another thing that I wanted to, the printing of the odometries at the end, just to say, hey, this is it. I'm done. I'm completed.
Sorry.
No, I mean, no. These are just points of I'm thinking about. But other than that, you accomplished everything. So congratulations, man.
Thank you.
All right. So I guess that's it then. So for everyone else that's watching, this is your opportunity as well. If you want to learn ROS and show the world how you've learned it, it's really hard to show your knowledge, especially showing code. For example, I come from a mechanical engineering background, so always I have this this not shame, but I'm nervous of showing my code. But I think this is sort of the final step in learning, is that, hey, here's what I did, and I'm comfortable showing it, and I know why I did this, so I put it up there. So for you guys that you want to do this and, get a certificate and keep pushing your programming skills and your robotic skill, you can do what Chengjing did here and present your project for the course that we have at the Construct. We have a bunch of courses that offer this presentation format, so I encourage everyone to go to our website, theconstructsim.com, and check it out. And Chengjing, again, thank you very, very much, and congratulations.
Thank you so much.
All right, guys. So that's it for us. We'll see you next time for our next presentation. Bye-bye, you guys. All right. Done.